Just think for a second about what your computer's doing right this minute. You've probably got a browser open, maybe some music playing, a dozen other things happening in the background, all of them fighting for the attention of one single CPU. So how does it manage all of that without just crashing? Well, today we're going to pull back the curtain on that little magic trick. We're talking about CPU scheduling.
Yeah, it's basically a digital traffic jam. Every single app, every process wants the CPU's attention, and it wants it now. And that brings us to the most fundamental question of all. With only one CPU and so many tasks demanding its time, who gets to go first?
So let's get into the CPU's juggling act. Now, this whole decision-making process, it's not random, not at all. The computer's operating system is kind of like a traffic cop. It uses a very specific set of rules, we call them scheduling algorithms, to make sure everything keeps moving and the system stays responsive.
We're going to zero in on two of the big ones, the absolute classic algorithms that pretty much everything else is built on: first come, first serve, or FCFS, and shortest job first, SJF. You can think of these as the original blueprints for how to manage that CPU traffic.
All right, let's kick things off with the most straightforward approach you can possibly imagine. First in, first out. This is the first come, first serve algorithm, and honestly, the name says it all.
I mean, the rule here is just so simple. It's absolute. The process that asks for the CPU first gets the CPU first. That's it. End of story. Processes are handled strictly in the order they show up. It's fair in the most literal sense of the word.
The perfect analogy is a ticket counter at a movie theater. If you get in line first, you get served first. It doesn't matter if the person behind you just has a quick question and you're buying tickets for your entire office party. The rule is the rule. No skipping the line.
So let's say person A shows up. They've got this super long, complicated request. Then, just a second later, person B gets in line with a really simple, quick task. Well, too bad for person B. They're stuck waiting until person A is completely finished. The only thing the system cares about is who arrived first.
Okay, so let's translate that ticket counter idea into computer terms. Let's say we have three processes that show up in this order: P1, then P2, then P3. As you can see, P1 is the heaviest lift. It needs 5 units of CPU time. P3 is the quickest one, needing only 2 units.
So, with that ticket counter rule in mind, how do you think FCFS is going to handle this? What's the order of execution going to be?
Yep, you got it. It's that simple. The algorithm doesn't care that P1 is the longest job. It was first in line, so it goes first. Then P2, and finally, the shortest job, P3, gets to run last. It's predictable, it's simple, and it seems fair. But, well, there's a catch.
And this is where this super simple, fair system kind of falls apart. It leads to a huge problem with a great name, the convoy effect, and it can seriously bog down your system.
Here's what happens. That big, slow process, our P1, is like a huge, slow-moving truck on a single-lane highway. All these other smaller, faster processes get stuck in a traffic jam right behind it. And what does that do? Well, the average waiting time for everyone just shoots through the roof. Suddenly, your whole computer feels like it's wading through mud.
Okay, so that whole convoy thing is a real drag, right? It got computer scientists thinking, what if we just ignored the line? What if we prioritize speed instead? And that brings us to our second algorithm, shortest job first.
So, SJF, or shortest job first, does exactly what its name implies. It just throws the whole first come, first served idea right out the window. Instead, it looks at all the tasks that are waiting in the queue and asks one simple question: who's going to be the quickest?
You know the perfect way to think about this? It's the express lane at the supermarket, right? It's designed to get people with just a couple of items through really, really fast, which helps the flow of the entire store. That's exactly what SJF is trying to do for your CPU.
All right, new scenario, same idea. We've got 3 new processes waiting. Check out P2. It's our express lane customer, needing only 2 units of time. And then you have P1, that's the big weekly shop. It's going to take 6 units.
So, thinking about that express lane at the store, how is SJF going to organize this workload? Who gets to go first? And boom, there you have it. SJF scans the queue, sees that P2 is the fastest, and runs it immediately. Then it looks at what's left, sees P3 is quicker than P1, so P3 goes next. And our big, slow P1? It has to wait till the very end. This is way more efficient, and the average wait time plummets. So we found the perfect solution, right?
Well, not so fast. SJF has its own pretty serious flaw.
a problem we call starvation.
Okay, so there are two huge problems with this. First, how in the world does the operating system know how long a job is going to take before it even starts? I mean, it basically has to predict the future, which is tricky. But the second problem is even worse. What happens to that big P1 process if a never-ending stream of little short jobs keeps showing up? Think about it. It could get pushed to the back of the line forever. It's literally starved of CPU time it might never get.
All right, so let's put these two head-to-head. We've got two completely different ways of thinking here. One is all about a simple idea of fairness, and the other is all about raw efficiency.
And this is really the heart of the matter, isn't it? It's a classic trade-off. You've got FCFS on one side. It's simple, it's fair, but you risk that awful convoy effect slowing everything down. And on the other side, you have SJF. It's super efficient, but you have to be a fortune teller, and you might literally starve important long-running tasks.
And this right here, this is the scheduler's dilemma. This is the fundamental problem that operating system designers have wrestled with for decades. It's not just a simple choice. It's a question about what you want to prioritize. So, I'll leave you with this question. If you had to build an operating system, and your only choices were simple but slow or fast but risky, what's the right call? And the truth is, this exact dilemma is why modern computers don't just use one or the other. They use really clever hybrid algorithms that try to get the best of both worlds. But, well, that's a whole other story for another time.